morning friends. Today let us learn about two special casting process. One is vacuum sealed molding process and the other one is the squeeze casting process. First let us see the vacuum sealed molding process. What is this? What is its history and what is its principle? This is also known as V process simply because vacuum is used. So, it is also known as V process, and this V process was developed in Japan in the year 1971. And what is the principle in this molding process? Free flowing dry unbonded sand is used to make the mold. You see, so this is a special characteristic of this process. In the conventional sand casting process, we prepare the sand by mixing the base sand, moisture, clay and some other additives. So, these are the ingredients of the conventional molding sand, but here free, dry and unbounded sand is used to make the mold, no moisture, no clay and no additives. Next, a specially designed strong polymer film is used to seal the open ends of the sand mold. The sand mold will be sealed using a strong polymer film. The vacuum inside the mold holds the sand rigidly in the shape of the pattern even after the pattern is removed. So, vacuum will be applied to hold the dry sand strongly and in the shape that is required by using vacuum. And here we can see the vacuum molding machine, and here we can see vacuum is applied here. So, this is the general setup of a V process or the vacuum sealed molding process. Now, what are the steps involved in V process? First step is place the precision pattern with the vent lines on a pattern carrier with a vacuum line, and here a wooden pattern is used. You see here. So, this is a wooden pattern, and on this pattern there will be several vent lines are there. Here you can see this is one vent line, this is another vent line, and likewise there are several vent lines are there. Now, all these vent lines are connected to the vacuum line, you see here. So, this is the vacuum line. Now, why these vent lines? Means this pattern, this wooden pattern will be covered with the strong polymer film, then the vacuum will be applied, and as the vacuum is applied, the polymer film will be sucked through these vent holes. So, that is the purpose of these vent lines. Second step, place a heat softened polymer sheet over the pattern. So, this is the pattern, and here we can see a kind of red colored one. So, this is the polymer sheet. So, this it should be heat softened and say it is kept over the pattern such that this sheet will be occupying all the corners and the details of the pattern. It will be here, then you apply vacuum here, then what will happen? Vacuum, as the vacuum is applied, the polymer sheet will be sucked. So, vacuum draws the sheet down to form a conforming polymer film on the pattern. As the vacuum is applied, the polymer sheet will be drawn, so that it will be sticking to the details of the pattern strictly. The next step, place flask with vacuum lines over the pattern. So, this is the flask. So, this flask also is attached to vacuum. Here you can see there is a vacuum line. So, this is a special molding flask. Now, this special molding flask with vacuum line should be kept around the or over the pattern. Fill the flask with very fine dry unbonded sand. Now, we have to place the fine dry and unbonded sand inside this flask. Now, it should not, there is no question of compaction as in the case of the green sand molding. Vibrate the flask to settle the sand into all the pattern's features. It should be vibrated, so that this fine and dry sand goes all around the details of the pattern. Next step is there must be some excess sand must be there. You can see here, say there is excess sand. So, this excess sand must be removed. So, level the sand and form a sprue cup. So, here a sprue cup is formed. Now, one more plastic film is to be kept. Place a plastic film on the top of the mold to form a vacuum tight seal. So, one more vacuum, one more plastic sheet is kept here and it is sealed here. You can see here it is sealed and this side also it is sealed, and previously we have used another one more polymer sheet. So, that is also sealed to the molding box here or to the special molding flask, and here on all the four sides the polymer sheet is closely sealed. Now, place a plastic film on the top of the mold to form a vacuum tight seal. Draw vacuum again, and here we have to draw the vacuum, apply the vacuum, draw the vacuum on the flask to rigidize the sand in the mold. Once we apply the vacuum here, what will happen? The sand will be held rigidly. So, that is the purpose of this second vacuum. Next one, release the vacuum from the pattern carrier. Now, here remember we are using two vacuums at two places. One is at the molding box, one is at the pattern. This molding box vacuum will be continued for some more time, but the vacuum which we have applied to the pattern will be withdrawn, will be released here. Then what will happen? It will be detached from the sand mold. Now, you see here this is the sand mold. Now, remember the sand mold is comprised of dry and fine sand, no moisture and no clay. Now, then the question is how it is bonded? Because of the vacuum. This sand now it is concealed by polymer film. At the top there is polymer film or the plastic film, at the bottom also there is plastic film. You see here, right down it is sealed on all the four sides of the flask. Here it is sealed and here it is sealed, here it is sealed and here it is sealed. Now, the pattern is withdrawn. Now, prepare the mold in a similar way to the drag also. So far we have seen how to prepare the mold for the cope. In a similar way we have to prepare the mold for the drag also. Now, these are to be joined, join the mold of cope and drag together to form the completed plastic lined mold cavity. So, this is the cope and this is the drag. Remember, this is the cope. For the cope, at the top and the bottom there is a polymer sheet is there, it is covered and concealed by polymer film. For the drag also, both at the top and the bottom there is polymer film and it is concealed by polymer film. Next one, after solidification and cooling of the casting, release the vacuum on the mold. Now, we have to pour the molten metal. Here we have to pour the molten metal. During pouring of the molten metal, this polymer film will be burnt, but the molten metal is straight away going. There is no gap between the molding sand and the molten metal. That is why the vacuum will be intact. So, the vacuum will be there and the molten metal will be filling the cavity. So, this continues, vacuum continues till the solidification is over, and after solidification and cooling of the casting, release the vacuum on the mold. Then what will happen? The unbounded sand will be dropping down. A clean casting with 0 draft and a 125 to 150 RMS surface finish will be obtained. So, this is the finished casting. So, these are the important steps involved in the vacuum sealed molding process. Now, what are the advantages of vacuum sealed molding? Simplified sand control. First of all, there is no sand control. In the case of the green sand molding, so we prepare the green sand by mixing base sand, moisture, clay and the additives. So, these ingredients are to be controlled very carefully, otherwise the molding sand may not have the required properties. So, here that sand control problem is not there, just take the dry sand and use it for the making the mold. So, simplified sand control. Next one, no sand reclamation means what is that? In the case of the green sand molding, after the casting is solidified, we have to shake out, means break the sand into pieces, the mold into pieces, then that sand has to be taken, again that should be crushed into small pieces. If any metallic pieces are included, those are to be removed. If any sand lumps are included, those are to be removed. So, this is the sand reclamation, again it should be conditioned with the moisture and a little more clay. This is the reclamation. Here there is no question of reclamation, straight away that sand can be taken and another mold can be made. No sand mixing is required, that is true. Next one, no waste sand removal. In the case of the green sand molding, every time when we pour the molten metal, little sand is wasted. So, here no waste of sand here. Next one, inexpensive patterns. Patterns are not very costly. Next one, no draft and other pattern allowances. In the case of the sand molding, green sand molding, we give draft to the pattern, so that during withdrawal of the pattern it would be easier to withdraw the pattern, and also pattern is given certain allowances, and here draft is not required, because we are not withdrawing the pattern the way we used to withdraw in the case of the green sand molding. Once we release the vacuum, automatically pattern will be removed. So, no draft is required, and other pattern allowances are also not required. So, that is how there will be minimum machining. Next one, reduced noise level. In the case of the green sand molding, there will be noise will be there, noise will be generated, sand will be mulled in a sand muller. So, that causes noise, and there will be sand conditioning plant will be there, because of that noise will be generated, and here no noise is generated. In fact, there will be very little noise will be there. Next one, better general environment. In the case of the green sand molding, we mix the sand, we mix the clay, we mix the additives, because of that there will be pollution will be there, and here there is no pollution, here there will be a better environment. Next one, reduced cleaning costs. In the case of the green sand molding, we have to take the casting by shake out, break the mold into 2 or 3 pieces, take the casting outside, then it should be cleaned, because sand will be adhering to the casting. By water cleaning or by pressurized air, the casting has to be cleaned. Here there is no such cleaning. Once we withdraw the vacuum, the casting falls down, and the sand here, as in the case of the green sand molding, sand will not be sticking to the casting. So, here the cleaning cost is reduced. Next one, reduce smoke and fumes. In the case of the green sand molding, because we are mixing clay and moisture, when we pour the molten metal, there will be smoke and fumes. So, that will not be there in the case of the vacuum sealed molding, and no shake out, you see here. So, just release the vacuum, the solidified casting will be falling down. No sand lumps, better finish on the castings, better dimensional accuracy, because we are not giving any what say pattern allowances, no draft allowance, and other allowances will be very minimum. That is how there will be better dimensional accuracy in the case of the vacuum sealed molding, and less energy consumption. Why? Because we are not running any sand muller, we are not running any sand conditioning what say plant, just to take the dry and clean sand and use it. That is how there will be lesser energy consumption. Next one, reduced pattern maintenance. In the case of the green sand molding, the pattern will be kept inside the molding box and sand will be compacted. Because of that, the pattern will be undergoing wear, or sometimes it will be damaged and it has to be repaired, or it must be replaced. In the case of the vacuum sealed molding, the pattern's life will be very longer, because we are not compacting the sand, we are not applying any mechanical force. That is how the life of the pattern will be longer compared to the green sand molding. Now, these are the limitations of the vacuum sealed molding. What are these limitations? One is skilled workers are required. Yes, in the right time the vacuum must be applied, and the vacuum must be applied to the required degree. So, that requires skill. So, that is how skilled workers are required. Next one, process requires vacuum. The vacuum machines, these are costly, and that is how the cost of the production goes up. Again, we use the polymer film to what say conceal the molding box, to conceal the molding sand, at both at the top and the bottom we use the molding film what say vacuum polymer film. So, that is how the process becomes expensive. Next one, rate of heat transfer is less compared to green sand molding. Why? In the case of the green sand molding, there will be moisture, because of the moisture the heat transfer would be maximum, but here there is no moisture in the molding sand. That is how heat transfer will be less compared to the green sand molding. But however, you can see here smaller sand grains can enhance the rate of heat transfer. So, we have seen that in the case of the vacuum sealed molding, we use clean and dry unbounded sand, but if the sand grains are smaller, so they enhance the rate of heat transfer. But remember that these sand, what say sand, this dry sand of smaller grains means small, what say the grain fineness number will be maximum or higher grain fineness number, such a sand's cost will be higher. Now, what are the process parameters of this vacuum sealed molding or the V process? Molding sand based variables: type, shape, size and sand distribution. Type means there are different types of the sands are there: silica sand, olivine sand, zircon sand. So, these are the types of the sands. Next one is the shape. The common shapes are the round, angular and subangular. So, these shapes also will be influencing the molding process. Next one, size and size distribution. Next one, plastic film based variables: type and thickness. Next one, vibration based variables: frequency, amplitude and time of vibration. What is the frequency of vibration and what is the amplitude and what is the time of vibration? So, these parameters would influence the quality of the casting. Next one, vacuum based variables. What is that? Degree of vacuum imposed. Next one, pouring material based variables: pouring time and temperature. What is the pouring temperature and what is the pouring time? These parameters would influence the quality of the casting. Now, here we can see Ishikawa diagram of the vacuum sealed molding process. So, here we can see there are 5 types of parameters are there. So, these are the sand parameters. So, these are the alloy parameters. So, these are the vacuum parameters, these are the plastic film what say parameters and these are the vibration parameters. Under the sand parameters, sand type, what type of sand it is it the silica sand, zircon sand, olivine sand, and here we can see this is the shape, is it angular, what is a round or subangular. Next one, what is its size, fine or coarse, size distribution. Next one, degree of vacuum, plastic film variables, type and thickness. Next one, vibration, time, amplitude, frequency and alloy, pouring temperature, pouring time. So, all these parameters would influence the quality of the casting. Important process variables and their typical ranges. Now, we can see here sand size 5 to 150 AFS mesh can be used, vibrating frequency 10 to 36 hertz, vibrating time 10 to 50 seconds, degree of vacuum 250 to 350 mm of the mercury. And here we can see a modern vacuum molding plant looks like this. Next one, again a modern vacuum molding plant looks like this. So, with this we are completing the vacuum sealed molding. Now, we will start the squeeze casting process. Squeeze casting process is also known as liquid metal forging. Squeeze casting is a method combining casting and forging technologies. What are the steps in the squeeze casting process? An accurately measured or metered quantity of molten metal is poured into a heated metallic mold. Here a metallic mold is used similar to the die casting, but there is a difference. The mold is closed to produce an internal cavity in the shape of the required component. The molten metal is displaced into the available space of the die cavity. After the molten metal is poured into the metallic mold, it is forced into the available space of the die cavity. Before that, the mold is given a coating, usually a graphite coating. Pressure continues to be applied till the molten metal solidifies and forms the required component. So, here we can see the basic difference between the what is a squeeze casting process and the die casting process. In the case of the die casting process, we apply the pressure so that the molten metal will be injected into the die cavity. Once the molten metal is injected inside the die cavity, we stop applying the pressure, but here the pressure continues to be applied till the molten metal solidifies and forms the required component. So, that is the difference between the die casting and the squeeze casting process. The press is then withdrawn and the component is ejected, and here we can see an illustration. So, this is the die, metallic die, and here this is the upper die, and here we can see the molten metal is poured into the die. Then the upper die comes down and presses. Yes, it has pressed here, we can see here, and remember this pressure will be applied till the molten metal is completely solidified. Yes, after some time the molten metal will be completely solidified, then the upper die will be withdrawn and it will be going up. Now this is the solidified casting. So this is the simple principle of the squeeze casting process. Now what is the classification of squeeze casting process? Broadly it is classified as direct squeeze casting and the other one is the indirect squeeze casting process. So two types, one is the direct squeeze casting and the other one is the indirect squeeze casting. Under the direct squeeze casting there are two more what say sub classifications are there, with molten metal movement, that is one type, another one is without metal movement. Under the indirect squeeze casting there are four types are there. One is the vertical clamping and injection, second one is the horizontal die closing and vertical injection, third one is the vertical die closing and horizontal injection, and the fourth one is the horizontal clamping and horizontal injection. First we will see what is this direct squeeze casting and what is this indirect squeeze casting. We will see the difference between these two and we will see the sub classifications. So here we can see this is the direct squeeze casting and this is the indirect squeeze casting, and here we can see this is the die, this is the die, and here also this is the die. Now this is the punch here, this is the punch, and here also this is the punch. Now the molten metal, this is the die and the molten metal is poured here and the punch is coming down and it is applying pressure on the molten metal, and here we can see this is the molten metal. So this is the feeding system. So this feeding system is not there in the case of the direct squeeze casting. So between punch and the molten metal there is feeding system. Now after the molten metal is filled with the die cavity, the punch comes down and applies pressure till the solidification is over. That is the difference between the direct and indirect squeeze casting process. So in the case of the direct squeeze casting, pressure is applied directly on the part being solidified. So this is the part being solidified and the punch is directly coming and applying pressure on the part being solidified. Yes, we can see in this diagram, but in the case of the indirect squeeze casting process, pressure is applied through an intermediate feeding system, and here we can see this is the feeding system. This feeding system is not part of the casting. Now the pressure is applied on this feeding system. Now this feeding system in turn will apply pressure on the part being solidified. So we have seen the difference between the direct squeeze casting process and the indirect squeeze casting process. Now let us concentrate on the direct squeeze casting process. So under the direct squeeze casting process we have two types, one is the with metal movement and the other one is the without metal movement. Let us see what are these. So in the case of the what say direct squeeze casting process, there are two types, we have already seen without metal movement and with metal movement, and without metal movement we see here. So this is the die, this is the die and this is the molten metal, and the punch is directly coming down and it is applying pressure downwards. Yes, here the punch is totally closing and it is applying pressure. After the what say application of the pressure, after the solidification of the component, the punch is going up, the component is rejected or it is ejected. Now what we can see here, there is no metal movement here, only application of the pressure, that is all, no metal movement. But in the case of the with metal movement category, let us see here. So this is the what say die and this is the molten metal and this is the punch. This punch comes down and applies pressure on the molten metal. As the punch is coming down, you see what will happen, the metal will be, some metal will be displaced from its previous position, you see here. So there is a metal displacement is there or metal movement is there, then the part solidifies. After solidification of the part, the punch goes up and the component will be ejected, this is the component. So these are the what say two types and the difference between the two subcategories of the direct squeeze casting process, with metal movement and without metal movement. So the one without metal movement is suitable for making ingot type components, whereas the one with metal movement is suitable for casting wide range of shaped components. Where we want to make only ingot type of components, there we can go for the first one, the one without metal movement. If we want some complex shaped components, then we have to go for the other one, means the one with metal movement. Now, we can see an illustration, direct squeeze casting with metal movement. Yes, this is the die and molten metal is being poured, the blue colored one is the molten metal. So, this is the upper die or the punch. So, this will be coming down and applies pressure on the molten metal, and here you can see it is squeezed, the molten metal is squeezed here and molten metal is solidifying here. After solidification of the molten metal, it is ejected, and here remember there is metal movement because of the complex shape of the component. Now, let us concentrate on the indirect squeeze casting process. So, in the indirect squeeze casting process there are 4 types: vertical clamping and vertical injection, horizontal die closing and vertical injection. Third one is the vertical die closing and horizontal injection, and the fourth one is the horizontal clamping and horizontal injection. Now, this is the vertical clamping and vertical injection, and here we can see. So, these are the dies. So, these dies will be closed vertically, and this is the injection, and the molten metal is coming here, and this is the plunger. This plunger pushes the molten metal into the dies and it will be pressing till the solidification is over. Here we can see vertical clamping and vertical injection. Next one, horizontal die closing and vertical injection. So, here we can see this is one die and this is one die. So, they will be closing horizontally. Then what will happen? So, here we can see this is the molten metal. The molten metal will be injected into the die cavity. So, here it is the vertical injection. Then after injection, so the pressure continues to be applied till the solidification is over. After solidification, the dies will be withdrawn and the solidified casting will be taken out. So, here it is the horizontal die closing and vertical injection. Finally, horizontal clamping and horizontal injection, and here we can see these are the dies, and they are closed clamped horizontally, and this is the punch. So, the molten metal is coming here like this, it is coming and it will be going inside the die cavity, and here there is a piston. This piston will be applying pressure on the molten metal and continues to apply pressure till the solidification will be over. So, here it is the horizontal clamping and horizontal injection. Now, development of the squeeze casting process. What are the steps involved? We have seen that squeeze casting is there are different types of squeeze casting process. One is the direct squeeze casting without metal movement, or direct squeeze casting with metal movement, or so on. What to use when? We can see here this is the block diagram for the use of the different process. So, here first we can use the direct squeeze casting without metal movement, means here the ingots or the blocks are made where there is no metal movement. Next one, direct squeeze casting with metal movement. After making the ingots, next we can make the parts. Here metal movement is there. Next one, vertical indirect squeeze casting. So, here also metal movement will be there. Next one, here we can see from there vertical and horizontal indirect squeeze casting plus low pressure die casting. So, these are the final process where we can get the final components. Now, what are the advantages of squeeze casting process? Parts of fine details can be produced. Sometimes we may come across components where there will be very fine details will be there on the component. Then what happens if we choose any other casting process? So, the molten metal may not fill those fine details. Here, because we are applying pressure on the molten metal, so the molten metal will be squeezed and it will be injected into those fine details. So, parts of fine details can be produced very easily. Now, shrinkage defects are very less. Why? Because we are applying pressure and the pressure will be applied till the solidification will be over. That is why there will be very less shrinkage defects. very high production rates comparable to die casting. No gating and riser, hence higher casting yield. There is no gating system here and also no riser. What is this casting yield? You see, casting yield is defined by weight of the casting divided by weight of the poured metal multiplied by 100. In the case of the sand casting, the casting yield will be 70 to 80%. Means if we are melting 100 kgs of molten metal, we can make only 80 kgs of the casting. 20 kgs of the molten metal is not used for making the component. As the casting yield becomes higher and higher, it would benefit the industry, but here the casting yield is 100%, produces the high quality surfaces. Because the molds are made up of the metallic ones, we get the very good surface finish. Next one, rapid solidification results in a fine grain size which improves mechanical properties. Solidification is very rapid. Why? Because the molds are metallic ones. Because the molds are metallic ones, they absorb heat rapidly. That is how we get the fine grains, and because of that there will be good mechanical properties. The amount of pressure applied is significantly less than used in the forging. Forging is the a process where we get very good mechanical properties, but the amount of pressure applied in the case of the forging is very much, is tremendous. That much force we need not apply here, but we get the almost same properties here. The amount of pressure applied is significantly less than the one which is used in the forging. Now, these are the drawbacks of squeeze casting process. Costs are very high due to complex tooling. No flexibility, as tooling is dedicated to specific components. So, that tooling means these dies are meant for making particular components. If we want to make some other components, these dies are to be changed. That is how the cost would go up. Process needs to be accurately controlled, which slows the cycle time down and increases process costs. Process needs to be accurately controlled. Next one, high production volumes are necessary to justify the initial investment. Sand casting, if we take even 5 components, 10 components can be made, but once we procure this squeeze casting machine, so high production volumes must be there, otherwise the cost we can't justify. Now, these are the typical applications of the squeeze casting. Now, it is commonly used for casting aluminum and magnesium alloys. Remember, squeeze casting is used for aluminum and magnesium alloys, and these are the typical components produced by squeeze casting process. You can see here. So, this is a fan blade. So, all these are made by squeeze casting process. A nickel produced by squeeze casting process. You can see here it has got very fine details, and this is produced by squeeze casting process. Now, what are the process parameters of a squeeze casting process? One is the casting temperature. Now, this casting temperature depends on the alloy and the part geometry, and this casting temperature should be 6 degrees to 55 degrees centigrade above the liquidus temperature. Next parameter is the tooling temperature. The tooling temperature will be ranging from 190 degrees to 315 degrees centigrade. Next one is the time delay. What is this time delay? It is the duration between the actual pouring of the molten metal and the instant the punch contacts the molten metal and starts pressurizing a thin melt. So, this is the time delay. Next one, pressure levels 50 to 140 megapascals are normally used. Next one, pressure duration 30 to 120 seconds has been found to be satisfactory for casting weighing up to 9 kilograms. Next one, lubrication. For aluminum, magnesium and copper alloys, a good grade of colloidal graphite spray lubricant has proved satisfactory when sprayed on the warm dies. So, what is the lubricant used? It is the colloidal graphite spray. Now, what is the difference between the squeeze casting and to its nearest casting process? So, now we have learned several what is a casting, what is a process. Die casting we have learned, gravity die casting we have learned, semi solid what say casting process we have learnt, and today we have learned the squeeze casting process. What are the difference between the squeeze casting and its nearest casting process? Now, first let us see the difference between the die casting and the squeeze casting. In the case of the die casting, pressure is applied while filling the mold cavity and not after filling. Yes, here also we use the metallic mold in the case of the die casting, and in the case of the squeeze casting also we use the metallic mold, but in the case of the die casting pressure is applied as long as the molten metal is filled with the inside the cavity. Once the what say cavity is filled with the molten metal, we stop applying the pressure. In the case of the squeeze casting, pressure is applied while filling the mold cavity and also after filling, not only during filling, also after filling till the cast component is solidified. That way die casting and squeeze casting are different. Next one, let us see the difference between semi solid casting and squeeze casting. In the case of the semi solid casting, the metal is poured between solidus and liquidus temperatures, whereas in the case of the squeeze casting, the metal is poured above the liquidus temperature, not below the solidus line. Now, let us see a comparison of squeeze casting with other process. Here we can see low pressure die casting, that is one, and let us take another process, high pressure die casting. Next, let us consider vacuum die casting. Next, let us consider Thixo molding. This is a semi solid what say casting process, semi solid forging, and finally this is the squeeze casting, which is today's subject. Now, let us consider some properties: cycle time, surface finish, gas entrapment, shrinkage pores, heat treatability and weldability. Now, in the case of the low pressure die casting, cycle time is average, surface finish is average, gas entrapment is average, shrinkage pores poor, heat treatability very good, weldability very good. In the case of the high pressure die casting, cycle time is good, surface finish very good, gas entrapment poor, shrinkage pores poor, heat treatability poor and weldability poor. In the case of the vacuum die casting, cycle time average, surface finish average, gas entrapment good, shrinkage pores poor, heat treatability very good and weldability very good. In the case of the Thixo molding process, cycle time is very good, surface finish is very good, gas entrapment good, shrinkage pores very good, means very what say shrinkage pores will be very less or may not be there may not be any shrinkage pores, that is the meaning. Next one, heat treatability very good and weldability very good. In the case of the semi solid forging, cycle time poor, surface finish very good, gas entrapment good, shrinkage pores very good, heat treatability very good and weldability very good. In the case of the squeeze casting process, let us see now, cycle time good, surface finish very good, gas entrapment very good, shrinkage pores very good, means shrinkage pores will be very minimum, sometimes there may not be any shrinkage pores, that is the meaning. Next one, heat treatability very good and weldability very good. Now, if we review all these what say properties and all these process, what we can observe? In the case of the squeeze casting process, every property is very good, only in the case of the cycle time it is good, otherwise all the properties are very good. So, that way squeeze casting is superior to its nearest casting process. Now, let us see the cost wise performance, a comparison of the component properties and cost. Let us compare the properties and the cost, and here we can see sand casting, here die casting, gravity casting, Rio casting, squeeze casting, this is the forging. So, these are the process we are considering now, and this is a graph where x axis represents the component properties and y axis indicates the what is a cost of production. In the case of the sand casting, the properties are poor and cost is also what is a very low. In the case of the die casting, the properties are better compared to the sand casting, but cost is little higher. Gravity die casting, the properties are better than die casting and cost is almost same, and in the case of the Rio casting, the properties are significantly improved and the cost is almost same. But in the case of the squeeze casting, we can see here properties are fairly improved, but the cost is little higher than the sand casting and other what say casting process. Now, here we can see this is the forging. Now, when we look at this forging, one thing we can notice, properties are very good. We can see these are x axis indicates the component properties are very good, but what about the cost of production? Cost of production is also very high in the case of the forging, but in the case of the squeeze casting, the properties are same as forging. You see, the properties are same as forging, but the cost of the production is almost 1/3 of the cost of the production of forging. That way it gives us very good mechanical properties at much lesser cost of production. So, this is the what say cost and properties comparison of the squeeze casting process. Now, again we can see a comparison of the squeeze casting with other what say process. So, this is what say we will consider squeeze casting, forging, die casting and sand casting, and here we can see the properties shape complexity, surface roughness, mechanical properties, dimensional accuracy, level of porosity, available for anodization, availability for heat treatment, productivity, needs for secondary machining and casting cost. And when we look at the squeeze casting, shape complexity very high, what say complex features can be obtained, surface roughness fair and mechanical properties are high, dimensional accuracy good, level of porosity few and availability for anodization good, availability for heat treatment good, productivity high, needs for secondary machining few, very few cases we need what say secondary machining, and casting cost is medium, not very high. But in the case of the forging, you see shape complexity low, surface roughness poor, mechanical properties high, dimensional what say accuracy fair, level of porosity limited, availability for anodization good, availability for heat treatment good, productivity good, needs for secondary machining very high and casting cost is very high, you can see here. And in the case of the die casting, shape complexity high, surface roughness fair, mechanical properties poor, dimensional accuracy good, level of porosity high, level of anodization poor, availability for heat treatment poor, productivity high, needs for secondary machining few and casting cost low. And with the sand casting, shape complexity is very high, surface roughness very coarse, mechanical properties fair, dimensional accuracy is very poor, level of porosity medium, availability for anodization poor, availability for heat treatment good, productivity fair, needs for secondary machining very high, next one casting cost medium. So, in that way also squeeze casting proves to be superior compared to forging, die casting and sand casting. Now, in today's lecture we have learnt two special casting process. One is the vacuum sealed molding process. So, here we use clean unbounded sand, dry and unbounded sand for making the sand mold, and for that purpose for what say rigidly holding the sand we have to apply the vacuum. So, that is how this is also known as V process. So, this gives us a very good environment and the cost of production will be very good, reasonable, and we have also learnt squeeze casting. And the squeeze casting we have seen there are two types, one is the direct what is squeeze casting and the other one is the indirect squeeze casting. Again direct squeeze casting is classified as with metal movement and without metal movement. Indirect squeeze casting is classified as vertical clamping, vertical injection, horizontal closing and vertical injection, vertical die closing and horizontal injection, and finally horizontal clamping and injection. So, with this we are completing this today's lecture, the what is a vacuum sealed molding and the squeeze casting process. We will meet in the next class. Thank you.